nanohub.org.
Online simulation and more for nanotechnology.
Okay, welcome everyone. Thank you for joining and welcome to our latest NanoHub hands-on machine learning and data science workshop. So this is part of our spring series. So I would like to welcome Kevin Greenman, who's a PhD candidate in chemical engineering and computation at MIT. Working in the group of in the groups of Professor Rafa Gomez Bombarelli and William Green. During his undergraduate studies at University of Michigan, he studied structural, thermodynamic, and optical properties of nitride semiconductors. He also has previous experience in developing NanoHub tools for research and education on computational catalysis during a summer he spent at Purdue. His current research interests are in using the combination of atomistic simulations and machine learning with experimental collaboration for the discovery and design of new molecules and materials. Okay, Kevin, thank you again for doing this workshop. Please go ahead and you can take over now. Thank you.
All right, thank you, Arun, for that introduction, and thanks to the rest of the team, Tanya, Aaron, and everyone else for this opportunity. So yeah, thank you for coming to this tutorial today. I'm going to be talking about message passing neural networks for molecular property prediction using a software developed at MIT called Chemprop. So to start off with, what is Chemprop? It's a Python software package that's developed completely open source on GitHub, and its goal is to train machine learning models to predict molecular properties. And the focus of what we're trying to do with Chemprop is to make it useful for scientists who have any level of machine learning exposure, so not necessarily people who are experts at writing their own models, but who have at least a base level of familiarity, but still in a very usable packaged way. And Chemprop is still actively supported. We still have a whole team of people who are working on responding to GitHub issues and also continuing development to add more features and improve the software. And before I go any further, I'd just like to acknowledge the rest of the team that's helped to develop this, because I've been actually just a minority of the work on the software so far. This software originally came out of a paper at MIT a couple years ago, led by Kevin Yang and Kyle Swanson. So you can see this reference for more details. And since then, there's been a whole team of developers who has been maintaining it and adding more features. It's a collaboration across many different departments at MIT, including computer science, chemical engineering, and materials science. And we're funded in a large part by the Machine Learning for Pharmaceutical Discovery and Synthesis, or MLPDS consortium. Now, a brief outline of what I'll cover today in the presentation. I will first talk a little bit about this directed message passing neural network, or D-MPNN algorithm, and why we think it's a good thing to use, why we built the package around it. Then I'll go over some information on how we format the inputs into the software, then how to do training, how to do prediction, how to do generating fingerprints using Chemprop, and then finally we'll go through and do a demo using a NanoHub tool in a Jupyter notebook. So when you're doing machine learning with chemistry, the first question is, how can you represent a molecule as a vector? Because a computer doesn't understand what a molecule is. A computer understands ones and zeros. So you have to represent it as some string of numbers. So that's typically going to be in the form of a vector or a matrix. And one way that that's commonly been done in the past for many years is using fingerprint representations, where one common way to do it is to look at different substructures that are present in the molecule and say, if this structure is present, I'll put a 1 at this particular index in the vector. If it's not present, I'll put a 0. Another way to do it is with substructure counts. So say the same structure is present 2 times, then you would put a 2 into the vector instead of a 1. So it could be a bit vector or a vector of integers. Another common way to do it is using descriptors, which are numbers that are often chosen by experts and thought to be relevant to the property that you're trying to predict. So these could cover any range of physical properties, but again are usually informed by some expert opinion and can be kind of painstaking to develop and figure out which ones are going to be the best. In contrast, a directed message passing neural network learns the vector that is used to represent the molecule, and then also learns the mapping from that vector to property. So in the previous method, we're using a fixed deterministic approach to get the vector to represent the molecule, followed by learning the mapping from that vector to the property, whereas with the D-MPNN, we're allowed to learn both. And the benefit here is that this is automatically generated, it's fully differentiable from end to end, which often leads to better predictions. So just to hammer this point home a little more, the light blue is meant to indicate in the vectors the starting vector. So you're starting with some vector for both the fingerprint. That's going to be the first vector, the leftmost vector in the middle, and then you are learning the vector that represents your property. And with the Morgan approach or some other fixed fingerprint, this vector in the center stays constant throughout the whole approach. Whereas with Chemprop, we are able to learn that vector in addition to the property vector. And the approach that it uses to do this is using a message passing algorithm. So it breaks down the whole framework into a message passing network and a feed forward network. In the message passing step, each atom is represented as a node of a graph, and each bond is represented as an edge. And then with each convolution operation, each atom learns something about its nearest neighbors. Then with the next convolution, its second nearest neighbors, third nearest neighbors, etc., for as many convolution operations as you wish to do. And then ultimately, once these atom representations are updated through each convolution, you do some kind of aggregation step to aggregate the atom level representations or the bond level representations to a single vector that represents the entire molecule. Then that vector is what is the input into your feed forward neural network, which is just a standard multi-layer perceptron, just the most basic kind of neural network, which ultimately is trained to predict the target. And our code here in Chemprop is written in Python using PyTorch. Chemprop can handle a variety of different data types and targets. So regression is one of the methods that we work with most commonly, but it can also do classification or multi-class. And then a special case of regression that we've worked with is molecular spectra, such as infrared spectra. The inputs that are required to Chemprop is something in a CSV file format. So you're going to have some header row that tells you which columns are smiles and which are targets. The smiles, if you're not familiar, is a way to represent a molecule using a string. So the letters typically represent the atom, but then there's different parentheses and other different symbols to represent branching, whether something's aromatic, etc. And you can look up documentation on that online, and there's plenty of tools available for converting from molecular structure to smiles. So if you have a smiles, you have a property, and you have a list of these, then that's enough to train a Chemprop model. And then to do a training step, there's a few required arguments. First, you're going to tell it that you're doing a regression task, or you're going to tell it the type of data that you're using, which in this example is regression. So here is where you would also be able to specify classification or multi-class or spectra. And we've also recently added a reaction type. You're also going to tell it where the input data is with the data path argument, and then finally where you'd like the results to be saved. There's several different hyperparameters that are important for a Chemprop model that control the number of convolutions that you do, that's the depth, as well as the sizes, numbers of layers of the networks, and a few other parameters. And these are all set to defaults that are generally, in our experience, good, but these should probably be tuned using some kind of hyperparameter tuning for any given application to get the best possible results. When you input a data file, Chemprop is able to automatically handle splitting that into the training set, which is what's used to learn the model parameters, a validation set, which is used to determine which epoch of the training to save that has the best validation loss, and then finally the test set, which is to evaluate the generalizability to some molecules that have never been seen before. By default, it's an 80-10-10 train validation test split, but you can change these as necessary. And if you wish to save these to a file, there's an option to do that as well if you want to look at which molecules are in each split outside of Chemprop. There's a few different methods for how to do the splitting. The default is just to split randomly. But as we've seen in some of the papers that we've published recently, random splitting is not necessarily a good test of generalizability. It might give you an overly optimistic measure of performance if you're testing on molecules that are very similar to your training data. So we have a number of different options available for data splitting to do more rigorous split strategies that give you a more realistic measure of performance. There's several different loss functions available, and they're grouped according to which data set type you're doing. So for regression, the default would be a mean squared error. There's other options available for classification, multi-class, and spectra. Chemprop also has the ability to handle multiple molecules for a given input. So let's say you have a molecule that exists in solution, and it has some property in that solution, but you're trying to make predictions on a set of molecules and solutions together. So in that case, maybe SMILES column 1 would be the solute, SMILES column 2 would be the solvent, and then you would have one or more properties for that solute-solvent pair. Another example could be mixtures. In chemical engineering, we're often interested in predicting a boiling point or a melting point of a mixture. So some people have done work on that using Chemprop, using this multiple molecule input approach. And when this is used, each molecule is represented by a separate message passing neural network, and those vectors are just concatenated before we make the final prediction. And to do a prediction, it's somewhat similar to the syntax for training. You're going to provide a test path that specifies where the molecules are that you want to make predictions on, somewhere to save it, and then finally a checkpoint directory which says where the model is that you saved from the training step. Another thing that you may want to do in addition to training and predicting is to extract the automatically generated fingerprint that I talked about from Chemprop and use that in something external. For example, to do some kind of dimensionality reduction, to do some interpretability on your model, or you may want to use it as input to some other algorithm other than the feed-forward network. So we provide this option for extracting the fingerprint, and it follows the same syntax as predict, but just using the different Python file. And you can extract the fingerprint at two different points. You can do it either in between the message passing step and the feed-forward step, or you can take the last layer of the feed-forward network as the fingerprint for a given molecule. Now wrapping up, just want to give a few heuristics that may be useful to someone getting started using Chemprop that we've learned over a couple of years of using it. The first thing is that Chemprop isn't always going to be the best tool to use. We know that especially for smaller data sets, it's most likely going to be perform not as well as a fixed fingerprint or descriptor representation, just because this type of neural architecture requires a lot of data to learn the interdependencies of the different atoms and the different local environments. Typically, if you have less than 1,000 molecules, we've seen that Chemprop does not perform as well, but it's still worth trying. And even if you're in a very large data regime, it's still important to benchmark Chemprop against other tools because it's definitely not guaranteed to be the best. If you're using an ensemble of different models, for example, to get an uncertainty estimate, we found that a size of 5 is pretty standard. And this typically gives you most of the benefit of using ensembles. So if you use 10 or 15 instead of 5, it's not going to improve the average prediction that much. Then if you're making predictions on or training on less than 10,000 molecules, you can probably just do this on a local computer. But if you're using a very large data set, it's probably important to have some kind of GPU available to accelerate the calculations. And with the GPU, you should be able to train generally in minutes to hours. Predicting is much faster, though. You can predict at about 1,500 molecules per second. So once you have a trained model, it's very easy to do inference very rapidly. There's a lot of other features in Chemprop that we won't be able to talk about today for time constraints, but there are features of cross-validation, hyperparameter tuning, different ways of doing the aggregation, as well as using additional molecule features in the fingerprint. So if you have some expert crafted features that you want to add in to make it better, you can do that. You can weight different targets or data points if you're more sure about some data points than others, if there's maybe a lower experimental uncertainty in measurement, or if you have targets that are at different levels of quantum chemistry theory, like you want to weight the more accurate theory better, you can do that. There's also some interpretation functionality based on the substructures, and also you can visualize using TensorBoard. So now, the last thing before I wrap up, just wanted to give a couple of examples of papers that have used Chemprop so far out of our groups, just to give you a sense of what Chemprop is capable of. It's been used to develop a discovery process for new antibiotics, to learn reaction properties using a condensed graph of reaction, to predict IR spectra, and then the last couple to predict solvation properties as well as ultraviolet visible spectra. So I encourage you to check out those references for more details, but this is just a small sampling of the uses that people have come up with Chemprop so far, so I encourage you to look into more. And then finally, just to point you to a few resources that you can go to after this tutorial is over if you want to learn more. There is our GitHub, which is completely open. It has a very extensive README that explains most of the key features. You can also look at the args.py file, which lists all of the possible arguments, and that's very well commented to explain what all of the arguments do. It's also a place where, of course, on GitHub, you can submit issues if you find something that doesn't work, if you have a feature enhancement request or anything like that. And this is also connected to a Read the Docs page that documents the tool extensively. So with that, I will switch over to the tool.
Okay, Kevin, thank you. Let's give everybody a minute to switch over. If there are quick questions in the meantime, please, attendees, feel free to ask them. So let me ask you a quick question from the chat, Kevin, before you start with the tool. Can this tool be used for periodic crystal structures?
That's a great question. So no, it cannot. There are very similar code bases available for that. I'm aware of some also developed at MIT, but generally this is only going to work for things that can be represented as a smile string.
Right.
But the message passing algorithm that underlies Chemprop is definitely applicable to those type of periodic or crystalline systems.
Real quick, how limited is the training set in this tool running on NanoHub? How many molecules are you considering?
Yeah, that's also a good question. So The tool that exists on NanoHub here, in its current form, it is just using some small sample data sets. So it's not structured in a way that that allows you to easily upload your own data. I think that is definitely something that's easy to do. You could, I think, just download the notebook from the demo and then go into the NanoHub tool for Jupyter using Anaconda, upload the notebook, and then from there you would be able to upload your own data sets and use it in that way. But I'm not sure what the computational resources that are available for NanoHub. So perhaps I would defer to others for that question.
We actually have a GPU available in NanoHub. It's restricted to a group. But I would just say let's go to the demo, and we have a forum, Q&A forum, so a lot of this discussion can continue over there in terms of follow-up work.
Yes, yeah. So we'll continue this discussion later. So Kevin, please go ahead with your demo. Yeah.
Okay, sounds good. So you can scroll past these first few cells. This is just a recap of some of the information from the presentation. So we'll start just by importing some of the necessary libraries, including Chemprop and some sklearn functions. Then the second cell, that's just utility function to do some plots later on. So we don't need to pay too much attention to that. So now we get to actually training our first Chemprop model. So here we just have a sample regression data set that we're providing as the data path. We're telling it the data set type, which is regression. We're providing a name of a directory where we want to save all of the smile splits as well as the PyTorch models that are saved. And then we're specifying the number of epochs we want to train. By default, it does 30, which I think typically you would want to do maybe between 30 and 100, but just for the purposes of the tutorial to make it go nice and quick, I just specified 5. So once we specify each of these arguments, this is just as a list of strings here, we can use the training argument parser to parse that list. And then finally use the train cross-validate function to read in those arguments and start training the model. So we'll go ahead and run that. So the output here, first it starts out just by printing all of the arguments. Tells you about loading in the data. So this, as I said, is a rather small data set just for testing purposes of just 500 points. There's only one prediction task. It's going to be the log of the solubility in this case. It'll tell you a little bit about your model. So these are all the default hyperparameters for the sizes of the different layers and the feed forward network. But still a good number of parameters, 300,000 parameters. Then it's going to start training, and by now, yep, it should be done. So in this case, we didn't use an ensemble. So the test RMSE of model 0 is the same as the ensemble test RMSE. And this plus or minus 0, this is if we had done cross-validation. This would give us a standard deviation across the different cross-validation folds. So that's hopefully gives you a good idea of sort of the anatomy of the output from Chemprop. So now we have a trained model file that's saved in the directory that we asked it to. So now we can make predictions on that. And because up here we specified this save smiles split argument, when Chemprop split the data into the training, the validation, and the test, it saved each of those to a separate file. So now we can specify that as this test smiles file and say that we want to save it in this CSV file. And then this is the file where our PyTorch model is stored. So you can run this. Prediction be very quick, done already, less than a second. And now we can visualize what these predictions look like in the form of a pandas data frame. So you can see the input is a smiles string and a log solubility, some floating point number, and then we have a list of predictions for each of those. So now we'll use that parity function to see how well we did. And see we're somewhat approaching parity here. Mean absolute error 1.23, root mean square error 1.65. So this isn't great. Of course, we want to be right on the parity line, but remember we only trained for 5 epochs here. So if you're interested, you can go back later, try training that longer, or maybe making the network larger. You can play around and see if you can improve this at all. Okay. So now there is also the option to predict using a list of smiles that's just within your Python script. You may want to do this if you have some other part of your Python script that is maybe generating these smiles or pulling them from somewhere else, such that they're not actually stored in a file. So to do that, you can specify the test path and the predictions path as the null directory, and you can provide a list of smiles in this format. When we do that, we see that it's still able to predict them, again, very quickly. Of course, this is only for 3 smiles, but so that is a useful way to do it as well. Another thing that may be of interest is to load a model once and predict multiple times. This may be if you have a workflow where you want to make a lot of different prediction steps, one after the other. The way Chemprop used to be set up is each time you would go to make a prediction, it would load the model again. And this was rather time consuming. So we adjusted the model or the Chemprop framework to allow you to load the model separately and then to make predictions on that model that is still stored. So if we have a couple different lists of smiles that we want to make predictions for, we're just going to use the train.load module once, and we can make predictions for both of those. Okay, so everything that I've shown so far has just been for making predictions on molecules, but I mentioned in the presentation that there's also the ability to make predictions for reactions. So here's a data set of reactions. So you're mapping to some activation energy, EA is the output. The input here is an atom mapped smiles. And I won't go into the details of how that's generated here. You can check the documentation for details, but essentially it's saying which atoms from the reactants and products are corresponding to one another, and it has both the reactants and the products in combined together in this smile string. So given the reactants and the products, you should be able to predict some property of that reaction, like the activation energy. So to do that, it's going to be very similar to the training syntax that we used before. So providing the first 3 arguments, which are the required ones, the number of epochs to make it a little faster. I'm going to save the smile splits. And then the only difference here is we're specifying reactions. So that's just telling Chemprop to expect this this atom mapped reaction smiles representation rather than the standard smiles representation. So we can make a training run here. Again, relatively quick, trained in 4 seconds. And the output is going to be essentially the same. So when we do predictions on that and we plot those to compare it to the predicted, you see here it does a little bit worse than predicting log solubility, but I wouldn't read too much into that. Again, this is just a toy data set and using a very quick training, so you can play around with that and see how you might improve that by training longer, changing different parameters. Now an example of predicting using multiple molecules. So here the CSV file looks similar as to the first part, except you have 2 different smiles columns and then some property that you're trying to predict. And in this case, the file is also a bit different because we're doing classification rather than regression. So we just have either a 1 or a 0 as the output. So here the differences in training, we're going to specify classification rather than regression. And we need to include this number of molecules is 2. Otherwise, it will get confused if it sees more than one column that are smiles. And there's also this argument called split key molecule that tells it which molecule to use for splitting. So by default, it's going to split based on the first column, but you can change it to split on any column of smiles that you provide. So an example of when you would need to do that is, I'll go back to what I was saying in the presentation about predicting on, say, a solute and a solvent property. Say that you have the same solute present in multiple different solvents, and you want to split just based on the solute rather than the solute solvent pair. So this would be a case where you would want to specify that. So we can run that training and prediction. And here again in the prediction, the difference here is you still need to specify that the number of molecules is 2. It doesn't know that a priori. But the output is generally the same as for the other prediction methods. Now we have different split types that we can do. So here I'm going to give an example of the scaffold balance split type. So this is this exemplifies a more rigorous splitting strategy. So rather than just splitting on the molecules that are present, you're splitting on their underlying scaffold. So sort of like the family that the molecule belongs to make it more rigorous. So it's not just that a molecule doesn't appear in the training and test set. You're trying to restrict it such that the test set doesn't have anything that's even close to what's in the training set. So you can train using this. Prediction syntax is the same. And then can plot the parity there. So here we see some similar results to what we did in the first set. However, you should notice these numbers here. So 1.36, 1.81 for the mean absolute error and root mean squared error. So just scroll back up to the first result that was using a random split. And you'll notice that these are lower, 1.23, 1.65 compared to 1.3, 1.8. So I think that's a good illustration of how splitting according to the scaffold is going to make the errors a little bit higher, but it's going to give you a more realistic idea of how well your model is going to do if you show it something that it hasn't seen before, which oftentimes in machine learning is the goal, to make a model that is generalizable. So now we'll move on to ensembling. So you can train an ensemble of models. When you do this, the different members of the ensemble are they're identical in terms of their hyperparameters, the structure of the model, but they are using different random initializations. And based on that different initialization, it will typically arrive at a different local minimum at the end of training. So this gives you often a better prediction if you take the average of the different members of the ensemble. That average prediction is often better than the prediction of any of the individual models. There's some kind of error cancellation that often happens there when using an ensemble. And the other advantage of using an ensemble is that in addition to the mean, you can get the variance of that ensemble. And the variance can be thought of as a measure of the epistemic uncertainty in the prediction, which is a way of saying the uncertainty in either the model itself or based on the coverage of the training data. So we will we'll train this on the reaction data set. We're going to use all of the same arguments that we did before. The only additional one here is that we're specifying an ensemble size of 5, which as I mentioned on the Heuristics slide, it is generally a good number of ensembles to use, or at least to start out with. So we'll train that. We'll expect that it will probably take 5 times as long since it's doing 5 in series. Should still be relatively quick, maybe 20 seconds or so. You can see the progress. Okay, great. So that finished training about 16 seconds. And now we can make a prediction. So predicting using an ensemble, if you're just trying to get the mean prediction, then it's going to be exactly the same syntax as predicting without an ensemble. But if you also want to calculate the variance of the predictions to get a measure of uncertainty, then you can provide this additional ensemble variance flag to the model. So do that. And then we can read in these predictions from a file into a data frame. So here the prediction file is giving you the input in terms of the atom mapped reaction smiles. It's predicted the mean value of the ensemble, as well as the epistemic uncertainty, or the ensemble variance, is going to be in an additional column with this epi-unc provided as or concatenated onto the name of the prediction variable. So we can generate a plot of those with some error bars. You can see in this case, most of the error bars are quite small, so it's actually not giving a very good measure of the uncertainty. Ideally, you would want a model that when the prediction errors are large, when the points are very far away from the parity line, you would also see very large error bars. But again, keep in mind here that this was a very quick training. So while the speed of the training and the way that we've trained it here is making the predictions bad, it's also making the estimates of the uncertainty bad. So you would expect that those uncertainty estimates, the error bars, would probably also improve as the model gets a better understanding of how to predict the data. But there's a whole active area of research into how to estimate uncertainty. That's a lot of what I'm working on right now, and that's you could do many different talks on that, so I won't go too in depth into that. But we are working on other methods to estimate uncertainty as well for Chemprop, and we hope to make those features available soon. So then another topic I want to talk about is the fingerprinting method. So here we're going to use a model that we trained in one of the previous steps that we saved in the test checkpoints regression file. But we're going to specify this additional fingerprint type argument, and we're going to say that we want to take the fingerprint from the message passing neural network. So that's the vector that's sitting in between the message passing network and the feed forward network. So we can run this prediction here. And just a sanity check to see what the shape of the output is. It's 500 by 300. That's because we had 500 molecules, as you may recall, in this first regression set. And then the 300 is the size of the fingerprint, which is specified as a hyperparameter, and that's just the default because we didn't specify one of those on our own. So that looks correct. And then just to illustrate what you might use this kind of fingerprint for, I wanted to show an example of dimensionality reduction, similar to something I've done in some of my own work to understand what the model is seeing, why it's predicting what it is. So we're going to do a principal component analysis to reduce this 300-dimensional vector down to 2 dimensions for visualization purposes. And then once we reduce the dimension, we can color each data point according to its property, according to its solubility. So you see here sort of a general trend of, as you move from the upper right of the plot towards the lower left, you see an increase in the log solubility. So this is giving you some insight into what the model is learning, how it's separating the space or mapping it onto a lower dimension in order to make effective predictions. And then next, we'll talk about predicting spectra. So as I showed in the presentation, there was an example of a paper coming out of our group to predict infrared spectra. And all of the code for that has been implemented into the main Chemprop branch now. So rather than, even though it is a regression task, we specify it with this unique data type called spectra. So then we can train as normal. The only difference here is we're also giving it some additional features. That's not necessary for predicting spectra, but just another illustrative example of something you can provide to Chemprop to help make predictions. So you can run that training. And then the test syntax or the prediction syntax is the same as before. An important note, though, is that if you provide features during training, you also need to provide features at test time. So we can predict using that trained model. And then our last step here is showing how Chemprop can be used for pre-training or transfer learning. So an example of when you might want to do this is if you have a computed data set, maybe generated using density functional theory or some other physics-based calculation, and you have a lot of these calculations, but then you have a smaller experimental data set, and the experimental ground truth is what you really care about, but you don't have enough of those data points to train a model on its own. So something that people often do in this case is they'll pre-train on the lower fidelity, lower cost data set, like a computed physics-based calculation, just to get the model close to the correct local minimum. And then they will use the higher fidelity, higher cost example that you have fewer of to fine tune the model, to adjust the parameters just a little bit to achieve the accuracy on the ground truth value that you care about. So to do this in Chemprop, we'll start out just by training another regression model here, just as we did before. Now, in order to take that regression model that we've trained, load it in and start training again based on a new data set, use this checkpoint frozen argument. You specify the path to the file that you're reading in. So in doing this, the checkpoint is not only going to be read in or loaded into your workflow, it will also be the parameters of the message passing network will be frozen. So the only parameters that will be allowed to change will be in the feed forward network. This is to ensure that the model isn't moving too far from the place or the local minimum that you've achieved with the large data set. You only want to be training a smaller number of parameters. So that's where that frozen comes in. So we'll train this new model and then finally make predictions based on that. So that is all of the functionality that I have to show you today, but I am happy to take any questions about any of these features that I've talked about or any of the other functionality that's available as well.
Thank you so much for that, Kevin. This question is, how much should be the loss function for good training?
So if I understand the question correctly, it's like what should the value of your loss be at the end of training? That's going to be pretty dependent on the property you're trying to predict. So if you're training, say, based on the mean squared error, that value is going to be very different depending on whether you're predicting a property that's very small or a property that's very large. So like, for example, we were looking at some solubility data sets where most of the numbers were in the range of maybe -10 to 10. Whereas some of the other data that I've worked with in the past has been for optical spectra. So you're looking at wavelengths and nanometers in terms of maybe 300 up to 900. So that's orders of magnitude difference. So that's going to depend a lot on your data.
All right, and then I do have one more question before I hand it off to Arun. This was another one I received. and it says, can you use polymers?
That's another great question. So it depends. It depends how you're representing the polymer. There's different ways to do that. Some of them I think are consistent with Chemprop's capabilities, such as if you're able to represent each monomer of the polymer as a smile string. So in that case, it might be applicable. But if you're not able to do that, or there's a lot of different monomers, then some other method may be more appropriate. That method could be analogous to this. Again, the message passing algorithm is very general, so could likely handle that type of data, but it wouldn't be naturally handled in Chemprop.
All right, thank you.
Okay, thank you, Aaron. There was a question about using the model for spectra, like, IR spectra, but you did cover that already, I believe. Let's take a look at this nice question from Professor Strachan, which I believe would be, helpful to everyone. Are you able to extract physical insight from the descriptors that you learned? And I think a related question I had was, are you able to use Chemprop to visualize the latent space, look for trends, using either just the fingerprints or with the properties, etc.?
Yeah, that's a great question. The answer is yes. We have been able to extract some physical insight, some interpretability of the models. That's why we initially put this fingerprint functionality in to extract those, because we were interested in asking this question, if we could extract physical insights. And something that I showed in my recent paper on predicting UV vis spectra is that when you visualize the latent space and you do some kind of dimensionality reduction, the points are at least somewhat clustered according to both their structural similarity. So if you color based on the different families of molecules that you're looking at, as well as the final property. In my case, the maximum absorption wavelength. You could definitely see some clustering based on that.
Okay. Yeah. Thank you. One question is about if we wanted to load our own data set, does the file need to be structured with the smiles and the quantity of interest in a certain order?
Yeah, another good question. So using the default arguments, it's going to assume that you have the smiles column first, followed by one or more property columns. But there are also arguments that you can provide that tell which column index to look at for both the smiles and the targets. So that is flexible.
Okay, cool, good. There's a question which says, how efficient is Chemprop? I'm not sure what exactly they mean. If you have an answer for that, Kevin, please go ahead.
Yeah, I mean, I guess it depends, of course, how you quantify the efficiency. Yeah. I mean, I don't have a clear answer to that. I mean, we don't make any claim that Chemprop is, the fastest or the best possible implementation. But we have found it to be quite effective for our purposes of training on, tens of thousands or hundreds of thousands of data points. I think even some people in our group have done in the millions without any issues. So I think it's at least efficient enough for our purposes.
Okay, good. So in terms of using it for polymers, polymers can also be represented with smile strings, but of course there's a periodicity element to them, based on how you represent them. So is this easily extendable to polymers? Is that what you would say? Or, there needs to be, a lot more work done in that area?
Yeah, I think similar to my answer to the first question on polymers, it sort of depends on the polymer. So I mean, if it's just a single linear chain of a single repeating monomer, like you have different examples of different polymers of that type, then I would say it's very easily extendable. But in cases where you have maybe different branching, or you have a lot of different monomers, I would say it would take more work to do that. But there's been some work also out of our group by Somesh Mohapatra in representing polymers using similar approaches to Chemprop. So I'd encourage you to look into that if you're interested.
Okay, yeah. The reason why I asked is, I mean, you do have, even if it's a single chain, you do have to consider periodic boundary conditions at that point, right? Which, would require a modification of your current framework, I assume, if you have periodic boundary conditions at all that come into the picture.
Right.
Yeah. Okay. So we do have some other questions. Which fingerprints are being calculated by the model? Not sure if if there's certain types of fingerprints that you're talking about. I'm not sure what the question is asking, but yeah.
Yeah. So the model, the fingerprint that's being calculated by the model is this automatically learned fingerprint. It's not using any kind of deterministic algorithm like a Morgan fingerprint or extended conductivity fingerprint that you may be familiar with. It's learning this just based on the back propagation in the neural network. It's learning the best possible fingerprint for making the property prediction. So this would be something that you could compare against a Morgan fingerprint or some other representation that's using a fixed deterministic algorithm.
Okay. Yeah, thanks. Can Chemprop work with co-crystals?
With what kind of crystals?
Co-crystals. Not sure if Bobby, if you want to expand on that, or
just like imagine a molecular crystal made out of two molecules, right? And you mentioned some cases, right, where you had a solute and a solvent. So co-crystal would be a crystalline solid with A and B type molecules arranged in a crystalline manner or amorphous manner for that matter.
Yeah, I think Chemprop could be applicable to that. I think it would depend. I mean, if you have, if it's going to depend on the crystalline structure, then I would say maybe it wouldn't be, Chemprop wouldn't necessarily be appropriate. But if you have maybe different amorphous mixtures of like A and B together, C and D together, then yeah, I think it could be applied to that. Another extension of Chemprop that we've been thinking about that isn't yet implemented, but we're working on it, is to weight the different fingerprints for different molecules according to, I guess, whatever you want to weight them according to. But one application would be weighting by concentration. So say you have the same two molecules, whether it's in a solution or in a crystal form, and you have different compositions. You would be able to weight the fingerprints according to that composition before feeding into the feed-forward neural network. So that could be an application there.
Okay, one more question I can see is, can you predict properties of natural products like chlorophyll and hemoglobin complex molecules? I guess a more general question would be, like, is it restricted to certain types of molecules, certain types of chemical constituents, or how widely applicable is it?
So it's applicable to anything that can be represented using a smile string is really the only restriction, because that smile string is what is used to transform the molecule into a molecular graph. And then that graph where the atoms are the nodes and the bonds are the edges, that's what's actually used for the message passing operations and the subsequent steps. So as long as it's representable as a smiles, then it is applicable.
Okay, yeah, thanks. If Aaron, Ale, if you guys have gotten any other questions sent to you, please, feel free to ask that. Sometimes I don't see all the questions here.
Yes, I've received two, and if you don't mind, I'll go ahead and ask those for the people. The first one I have is, I am using Google Colab for training for my final year project. But as it is a platform that already consists of a script, is it right to do so because I am not learning much from that?
Sure, yeah, I can answer that. So, I mean, yeah, for the purposes of Colab, if you're interested, we do have a Colab demo within the GitHub repo if you want to use Chemprop based on that. There's some weird things that you have to do with installing dependencies for it that we've figured out for you. But yeah, just in general, Colab is good, or Jupyter is good for getting started and getting a feel for some of the basic functionality. So maybe for a final class project or something like that, that might be an appropriate level of abstraction. But if you're really trying to learn the details of what's going on in the model, then I don't think Colab or Jupyter is going to allow you to do that.
And I would say you always remember NanoHub, and you can use NanoHub as well.
Mm-hmm.
Yeah.
And I got one more. Thank you for the interesting presentation. Have there already been attempts to utilize the tool for predicting NMR spectra?
Yeah, that's another good question. So I believe that there was some work done in that space at MIT a year or two ago. I can't remember off the top of my head if or where it was published, but I think people have looked into that at least a bit.
So thank you once again to Kevin Greenman from MIT, for a great presentation and a demonstration of the tool. Ale,
again, thanks so much, Kevin. This was a really nice presentation. Thanks everyone for joining in.
Thank you. Thanks, Kevin.
Yeah, thank you all.